WTW124 2021 semester test 1. So let's go look at the first question. So they give us these two equations, then they ask us to calculate what is vector A times vector B. So there are a lot of methods to use, but I'm just going with something that seems easy at the time. Is equal to this vector, and then 2A plus B is equal to 7, 3, and 5. I'm quickly going to subtract these two. So 3A minus 2A is just A, and then this is B. So 12 minus 7 is just 5. 5 minus 3 is 2, and then 8 minus 5 is 3. Okay. So now our goal is to multiply A and B, not add them. So let's go get B alone. Okay, so we can manipulate this one, multiply it by 2, then we might get the A alone. So we have this that they gave us, 12, 5, 8. Let's multiply this entire row by 2. Okay, and then 10. And then we subtract it as the sign suggests. So this will be minus A, which is equal to minus 2, minus 1, minus 2. So we know that A would be 2, 1, 2. Okay. If we try to work out B, it's just 5 minus 2, which is 3. 2 minus 1 is 1. And then 3 minus 2 is 1. So if I multiply these two with a dot product, then it would be 3 times 2, which is 6, plus 1 times 1, plus 1 times 2. And this will be 9. So the correct answer is B. Number 2. Okay, so this is a magnitude question, and they give us two rays, and these rays have the same origin. So then we can actually work out a magnitude of the angle formed by these two rays. Okay, because there is a point of intersection. The point of intersection is 0, 4, 0, and then we can work out this, let's call it theta. Okay, so the formula to calculate that is cos of theta is equal to a directional vector times another directional vector over P, the norm of P, and then the norm of Q. Okay, so P times Q in this case is this times this, which is 0, 0 times 0, plus 1 times minus 2. So that's just minus 2. Okay, and then the norm of this will be square root of square root 3 squared, that's just 3, and then plus 1 squared, which is just 1. And this will just be minus 2 squared is just 4. Okay, so at the moment we have cos of theta is equal to minus 2 over 4, which is minus a half. So if we calculate theta, we say arc cos of a half, then we'll get theta is equal to 2 pi over 3. So the correct answer is A. So at 3, they tell us there is a Cartesian plane and it has this specific equation. And they tell us there's a line with this specific equation. And they tell us that P is the point where this line and this Cartesian plane intersect. Okay, so usually I just like to simplify this line so that I have only the 3 components all in one. So this x I'm just going to simplify it, say 2 plus t and 1 and then 1 plus 2t. Now, this line and this Cartesian plane will intersect where the x components, y components, and then z components are all the same. So, in other words, I can put this x into this x. Okay? So 2 times 2 plus t plus 3 times the y component, which is 1, plus the z component, which is 1 plus 2t, must be equal to 20. So at this t value, the two lines will intersect. So 4 plus 2t plus 3 plus 1 plus 2t is just equal to 20. So 4t is equal to 12. Yes. So the t will be equal to 3. Okay, so let's go work out what will be the value of p then. So they're equal for t is equal to 3. So p will be equal to 2 plus 3, 1 plus 2 times 3. So the p coordinates will be 5, 1, 7. And they ask us what is the value of p3. So this is the last component. So the answer will be 7. Number 4. Suppose x, y, z are real numbers such that these are equal to this. Determine z. Hint, first find x and y. Okay, so first we can see there is a cross product between these two. So what I like to do is I like to write the numbers like this beneath each other, and then I work systematically according to this. So 2 times y minus 3 times 1, and then x times 3 minus 1 times y, and then lastly 1 times 1 minus 2 times x. Okay, they tell us this thing is equal to this. Okay, so first of all, this component, let's go work that out quickly. So the first components are 2y minus 3 is equal to 1. So we can easily find y, because 2y is equal to 4, so y is equal to 2. So if we go look at our second component, 3x minus y is equal to 13, 3x minus 2 is equal to 13. So 3x will be equal to 15 such that x is equal to 5. And now in 3 we have 1 minus 2x is equal to z. So 1 minus 2 times 5 is equal to z. So 1 minus 10 is z. So z is equal to minus 9. And this gives us D. And that is the correct answer. Perfect. Now, consider the points P, Q, and R. Which of the following statements are true? So we need to go test these. Okay. So R is between P and Q. Okay, so to test if R is between P and Q, we need to do the following. So we need to check, is R 1, 1, 1, is it equal to, let's choose one of these points as a starting point. Let's say P plus T and then q minus p. So 0 minus 2, 2 minus 0, and then 0 minus 2 again. For some, for t is actually between 1 and 0. Okay, so this will only work. This will only be between those two if t is between 0 and 1. So let's go test this series. So 1, 1, 1, and this side we have 2 minus 2t, 0, 0 plus 2t, which is just 2t, and then 2 minus 2t. So for our first component, we have 1 is equal to 2 minus 2t, and this will be minus 1 is equal to minus 2t. So t will be equal to a half. So far it works. Okay, for our second component, 1 is equal to 2t. So far it works still. For our last component, 1 equals to 2 minus 2t. And this is the same as the first component. So t is equal to a half. So r is definitely between p and q. Perfect, so this works. And so because r is between p and q, anywhere between, but this half suggests exactly in the middle, because t is between p and q, because r is between p and q, that means that all of these coordinates, all of these points, all of these vectors should be on the same line, okay? Because it can't be p here and then a q here and then r here, because how would you define this? If r isn't even on this line, how would it be between them? R could might as well just be here. Okay, so for this to work, R needs to be on that line. So Q is on the line through R and P. Yes, this is correct. And then also R is on the line through P and Q. I mean, all of these are on the same line for this betweenness to work. Otherwise, these T values would not be the same. Okay, so all of these are correct. The correct answer is D. Okay, so it's D. So section B, question 6. Let L1 be a line through the points PQ. Okay, only 2 points. Let L2 be a line through points A, B. Let vector R be a point of intersection of the two lines. Determine R. A full motivation is expected. So let's go write the formula for L1. So L1 is equal to, let's pick any one of those, 1, 2, 0, plus with 2, and then 5 minus 1 is 4, and then 6 minus 2 is 4, and then 8 minus 0 is just 8. For some t is the element of R. And then let's simplify it even further. So 1 plus 4t, 2 plus 4t, and then 8t. This is line 1. Now line 2 is 4, 5, 2 plus t. 0 minus 4 is minus 4. 1 minus 5 is minus 4. And then 2 minus 2 is 0. Let's rather make this a S because we don't know if these lines intersect. So we can't assume they're in the same plane. So this will simplify to 4 minus 4s, 5 minus 4s, and then 2. Okay. So for R to be an element of line 1 and line 2, Okay, so I want to say the components need to line up with each other. So this has to be equal to this. Second component should be equal to this component. So for R to be an element of L1 and L2, first equation that should hold would be 1 plus 4t is equal to 4 minus 4s. Okay, so let's just simplify this a little bit. If you take over this 4, it becomes minus 3 plus 4t is equal to minus 4s. If we divide by minus 4, we get 3 over 4 minus t is equal to s. So for our second component, we have 2 plus 4t is equal to 5 minus 4 times s. But now we have something for s. We have this. Okay, 4 times s. Let's go to substitute it correctly. 3 over 4 minus t. So this will be 2 plus 4t is equal to 5 minus 3 plus 4t. Okay, so if we take this over, we will actually get 0 on this side. And then on this side, we'll also get 0. So this tells me that there are infinitely many solutions so far, because 0 is equal to 0, and we can't find anything for s. But now let's go quickly look at number 3. 8t is equal to 2. So this tells me that t should be equal to 1 over 4. Okay, so if I go substitute this back into this one, back into 1, then we get 3 over 4 minus 1 over 4 should be s. And that just gives me a half is equal to s. Okay, so now let's go plug those values in, because this basically just tested that this actually works. So R is then equal to 4 minus 4s, then it's 2 plus 4t. You can use any one of these. So I used this by the first one, and then I used the second component. Oh, I used this as my first component, and then this is my second component, and then let's use this as our last one. So 8t. 8t. Okay, so our R will be 4 minus 2, which is just 2. And then this should be 2 plus 1, which is 3. And this would be 2. Okay, so our answer for number 6 should be 2, 3, 2. Okay, and we must actually check this. We must go check and see, does this work? Let's actually go check these answers by just employing them in step 2. Okay, so in step 2, we got 0 is equal to 0. So let's test it in this one, because this is a bit sketchy. Okay, so our second components should be equal to each other. So left-hand side, this is just a check, is 2 plus 4t, and t is 1 over 4. So our left-hand side is equal to 2 plus 2 plus 1, which is 3. And our right-hand side is equal to 5 minus 4s, and this is a half. So this will be 5 minus 2, which is 3. So left-hand side does equal our right-hand side. So this actually works. This is our final answer. 2, 3, 2 is the point of intersection. Now 6.2, let theta be the magnitude of the angle at vertex R. Okay, so this is the point where they actually intercept. Um, with vertices ARP, so we have vertices ARP, and R we have as 2, 3, 2. This is vector what, R, and then A they gave us as well is 4, 5, 2, 4, 5, 2. This is A, and then P they also gave us it is 1, 2, 0. This is vector P. So this is basically a ray that goes from R to A and then from R to P. Determine cos of theta. So this is the angle that is formed. Okay, so draw the triangle and leave your answer in exact form. So let's go to find rays first. That's how we determine magnitudes. So ray 1 is equal to 2, 3, 2 plus 4 minus 2 is 2, 5 minus 3 is 2, and then 2, that's that one. So let's make this k. And this is directional vector because it's a ray. Okay, so, okay, and this is for k greater to equal to 0 because it is a ray. Okay, it's not a real number, k is just greater than 0. And ray 2 is an equal to 2, 3, 2. And then directional vector, let's say this is x. 1 minus 2 is minus 1. 2 minus 3 is minus 1. 0 minus 2 is minus 2. And this is for x greater than 0 or equal to 0. Okay, so we take this directional vectors. And then we use that to work out the magnitude of theta. So it's just going to be this 2, 0 multiplied by this. So 2 multiplied by minus 1 is minus 2 over the how big this is. The magnitude of this one alone will be 2 squared plus 2 squared in a square root. And this one will be 1 squared plus 1 squared plus 2 squared. Okay, so this is minus 4 over 4 plus 4 is 8. And then 4, 5, 6. Okay, so this is what we have so far. Minus 4 over square root of 48, which is just 4 square root of 3. So all in all, we have this. And with this, we can calculate our theta by saying arc cos of minus 1 over square root of 3. Okay, so it's not even needed to calculate theta because they ask us to just calculate cos of theta. Okay, so let's just multiply above and the top with the square root of 3. Then we'll get negative square root of 3 over 3. And that is our final answer. Okay, and now 6.3, you can assume there is a unique plane P that contains line L and line 2. Knowing this, write down a vector equation for this plane. Okay, so basically this tells us that there are these two lines. Okay, remember they intersect here at 2, 3, 2, if I'm not mistaken. 2, 3, 2, yes. And there's a plane contained within these lines, line 1 and line 2. Okay, so it's actually quite easy to write the formula for this. So P will then be equal to, let's see. Oh yeah, firstly, just a small notation mistake. There where I made lines, this should be in brackets, in curly brackets. Okay. Otherwise, it's wrong. Okay. Otherwise, I could have just said X. Then I could state this. Otherwise, I can't say it actually like this. So the here also, R should be defined as a set. Okay, so P is then a point of origin. Okay, and that is 2, 3, 2, and then plus, let's say, T. And then we have to choose a point on one of these lines. So one on this line and one on that line. So let's say P 1, 2, 0, 1, 2, 0, and then line 2, let's say 0, 1, 2, 0, 1, 2. Okay, so now we're just gonna say this minus the point of intersection. So 1 minus 2 is minus 1, 2 minus 3 is minus 1, and then 0 minus 2 is minus 2. Okay, and then plus another one. Remember, there's two lines we have to parameterize. So S will be 0 minus 2 is minus 2, and then 1 minus 3 is minus 2, and then 2 minus 2 is 0. And this is all for ST's element of R. And that's how I would define this plane. Okay, and obviously, again, you can write this as a vector without the curly brackets. So yeah, that was just a small notation mistake. But just remember also a plane has two perimeters defining it. Okay, one on the one line and one on the other line. And this is for the two perimeters, S, T's element of R. Okay, and now question 7. Let P be the plane with Cartesian equation this. Let Q be the plane with Cartesian equation this. Determine any point A satisfying that A is an element of P but not an element of Q. Okay, so this is kind of trial and error to test what vector will actually work for P but not work for Q. Okay, so let's choose another one, a random one. Let A be equal to, let's say, 5, 0, 1. Let's see if it works. Just let's go make sure it works for P, definitely. So if I say the X component is 5, this is 0, what should Z be then? This is 5, this is 0. So our Z component would be 3 minus 5 divided by 2, which is minus 1. So this works for P. And we know that A is an element of P. But let's see if it works for Q. In Q, 2 times 5 plus 0 minus 1 is equal to 10 minus 1, which is equal to 9. And 9, since 9 is not equal to 5, this vector is not an element of Q. Okay, so I take a vector that actually works for P, so I plug in anything in these two and see what that gives me, and then I plug those same values into my next equation and see if it gives me the right answer. And if it doesn't, it's not the same. Okay, so this point is on P but not on Q. For the next question, determine any point P is an element in reals 3, satisfying P is an element of both P and Q. Okay. Okay, so for this question, we have to find a point that are both on P and Q. Okay, on the Cartesian plane P and Cartesian plane Q. Okay, so there are many methods to do this. I'm going to do one that looks easiest for me at the moment. So x plus y plus 2z is equal to 3, I think. Yes. And then 2x plus y plus z is 5. So what I'm going to do is I'm going to write a formula, everything in terms of x. So I'm going to get y with something in x and z with something with x. So first of all, let's quickly get something with z by cancelling out these y's. Okay, so let's subtract this. So what will happen is x minus 2x will give us minus x. This will cancel out, and this will become plus z is equal to 3 minus 5, which is minus 2. So if we get z alone, z will be equal to minus 2 plus x. Okay. Now let's try to get something with y alone. So what I would do is I would multiply with 2 to cancel these two out. So this will become 4x plus 2y plus 2z is equal to 10. And we subtract. So this will become minus 3x. This will become minus y. And this is minus 7. So y will be equal to minus 7. This sign will actually change. So 7 minus 3x. So P will be equal to something like T 7 minus 3t and then minus 2 plus t for t is the element of R. Okay, cool. So let's say for t is equal to 0, P is equal to, it will actually be equal to 0. 7 minus 0 is 7 and minus 2. Okay, so let's just quickly show that this is actually a point on P and a point on Q. Okay, so test on P. So 0, the left hand side is equal to 0 plus 7 plus 2 times minus 2. And this is equal to 7 minus 4. And 7 minus 4 is 3. Cool, perfect. Right hand side is also equal to 3. Thus, P is equal to 0, 7 minus 2 is an element of P. So now let's test on Q. Let's see if it's actually on Q. So the left hand side will be equal to 2 times x, which is 0, plus 7 plus minus 2. So it's just 5. And this right-hand side is also 5. Thus, P is equal to um, 0, 7 minus 2 is also an element on Q. So this actually works. Perfect. So now 7.3 asks us use 7.1 and 7.2 with an appropriate theorem and motivate to describe what object P and Q is. Okay, so since P and Q are planes in real 3 and they intersect at P is equal to T 7 minus 3t and then minus 2 plus t for t is an element of R. P and Q is a straight line. Okay, so since P and Q are planes in 3D and they intersect at this for t's element of R, P and Q is a straight line where P and Q intersect. It's a little bit redundant and over the top, but yeah, I'm just emphasizing that this is the place they intersect and that is a straight line where they intersect. Okay, now 7.4, determine another point, Q is element of R, satisfying Q is element of P and Q, where Q is not equal to P. Okay, another point, Q, satisfying this. Okay, but it can't be equal to P. Okay, so let's say Q. Okay, so we can do anything now actually. We can say at T equals 1. So for T equals 1, Q is then equal to, let's just replace a 1 in here. So Q is 1, 7 minus 3, and that will be 4, 7, 4, and then minus 2 plus 1 is just minus 1. So that is actually another point where they intersect. Okay, and we can actually go and test this. We'll do that in a bit, but I just want to make sure from this, from they ask us actually to reference 7.1 and 7.2. So 7.1, it just states that P is not equal to Q, so that these are not the same planes. Okay, it's not the same planes. And 7.2 actually shows us that P and Q is not an empty set. Okay, so they actually intersect. And because there are more than 2 points on this planes that intersect, um, then it is a straight line. So this is by the bucket theorem. The bucket theorem. Okay. So now let's go back to this. Let's go test. Test P. Okay. So P is then 1 plus 4 plus 2 times minus 1. This is the left-hand side, remember? So it should be 3 at the end. Let's go test. So this is 5 minus 2, which is indeed 3. So the left-hand side is equal to the right-hand side. So this Q is an element of P, and then test Q. So the left-hand side is then equal to 2 times 1 plus 4 plus 1, which is minus 1. So 2 plus 4 minus 1 is just 5. And then also the right-hand side is also 5. So Q is then an element of Q. And Q is not equal to P, and that's what we wanted. At 7.5, they ask us to determine P and Q. Write down your answer in set builder notation. So they actually want us to write a formula for this. So that's quite easy because we just determined 2 points where they actually intercept. So if we have 2 points, we can easily determine a formula for this. So let's say P and Q is equal to. So let's do a starting point as 1, 4, minus 1, 1, 4, minus 1, plus with T, and then we take P minus T. So 0 minus 1 is just minus 1, and then 7 minus 4 is just 3, and then minus 2 plus 1. Minus 2 plus 1 is minus 1. Okay, so this will be our formula for the line where P and Q intercept. Perfect. So now let's go to question 8. Question 8 actually asks us, let L1 be a line through P and Q. Let L2 be a line through A and B. For some unknown values A and Y, if line L1 and line 2 are parallel, determine the values of X plus Y. Okay, so now L1, let's quickly go define how that looks. So L1 is 2, 1, 1 plus T 1, 3, 2 for T's element of R. Okay, and L2 is equal to 1, 2, 2 plus S. Yeah, we can actually use the same or different parameters here. I just try to use different because it's not to say that these are on the same plane. Okay, so 1 minus X, 2 minus Y, and 2 minus 8. Oh, I did this the wrong way. It's X minus 1, Y minus 2, and 8 minus 2 for some H's element of R. Okay, so now we have two formulas. Okay, and we want to determine where are these parallel. So if these lines are parallel, determine the value of X plus Y. So if they're parallel, it means that these two are scalar multiples of each other. So since L1 and L2 are parallel, then 1, 3, 2 is equal to alpha x minus 1, y minus 2, 6 for some alpha is element of R. Okay, so for our first one, we say that 1 is equal to alpha x minus alpha. From our second one, we have 3 is equal to alpha y minus 2 alpha. And from our third one, we actually have 2 is equal to 6 alpha. So we can determine our alpha from the third equation. Our alpha will then be 1 over 3. Now let's get substituted into this one. So 3 is equal to 1 over 3y minus 2 over 3. And then we can actually calculate our y. So if you say 3 plus 2 over 3, we have 11 over 3 is equal to 1 over 3y. And if you multiply both sides by 3, we actually get our y as 11. Okay, so our y might be 11. And then if we substitute our alpha into this one, into 1, we have 1 over 3x minus 1 over 3. So if we say 1 plus 1 over 3, we actually have 4 over 3 is equal to x over 3. So x is equal to 4. Thus, x plus y is equal to 11 plus 4, which is 15. And now question 9, for which values of m is the element of R is this vector parallel to the plane with the Cartesian equation this? So let's think of the Cartesian plane as a piece of sheet of paper, and we want this vector to be parallel to this plane. So something that goes over the paper. So that means the normal of this paper should actually be perpendicular to this vector. So for x to be parallel to P, then x should be perpendicular to the normal of P. So x should be perpendicular to the normal of P. Okay. So for this to be possible, thus x times this normal should be equal to 0. Okay. The reason for this is cos of 90 degrees is equal to 0. So that's something perpendicular. Okay. So this x coordinate is just m minus 1, 2. Luckily, it's just dot product. It's not cross product. And then the normal is just m, 1, m. Yes. Okay, so now we actually need to multiply these two to get us 0. So this is m squared minus 1 plus with 2m is equal to 0. So in standard form, this is how it should look. So if we factorize this, it will be impossible. So our m would be equal to plus or minus 2 plus or minus 2 squared minus 4 times minus 1 over 2. So our m would be minus 1 plus or minus 4 plus 4 is 8, and square root of 8 is equal to, I think, 2 times square root of 2 over 2. So m should be equal to minus 1 plus minus square root of 2. And that is exactly the right answer. Okay, so if our m is minus 1 minus square root 2 or minus 1 plus square root 2, then this will be parallel to this sheet of paper. Okay, perfect. I think we explained everything very well. We said this is equal to 0 because cos at 90 degrees is indeed 0. So now for question 10. So here at question 10, they provide us with a theorem and with a few steps on how they solved this theorem. Okay, and now at 10.1, they ask us to prove that step 1 is true by doing a short calculation with reasons. You must mention the appropriate dot product properties that you use. So as we can see here, they squared this. So let's go see how we can simplify this. So by a few definitions we've learned, we know that this is just equal to this inside vector multiplied by himself, well, dot product with himself. Okay, this is basically just saying that the norm of v squared is equal to v dot v. Okay, and then next they just distributed everything by using FOIL basically. So x dot x plus 2x dot y plus y dot y. Okay, and they use the distributive or distributivity of let's say distributivity of dot product. Okay, so it's a dot product and we distributed everything. And this is again just equal to this again. And this is equal to this again. By using that exact rule we used at the start. Okay, and that's how they got this at 10.1. At 10.2, why does step 3 follow from step 1 and 2? Okay, so step 3, we want to prove this. How does this follow from the previous ones? Okay, so for 10.2, we start by saying, okay, they ended up with this again, this x plus y everything squared. We know now that it's equal to this. Okay, because we've done this in the previous steps. This is from step 1. Step 1. Okay. Next, we can actually use the Cauchy-Schwarz inequality for this part. Okay, and put it in absolute signs. So this stays the same, but this we can actually change to an absolute sign. Okay, this is from the Cauchy-Schwarz. Cauchy-Schwarz inequality. I don't think the spelling is correct, but you know what it means. Cauchy-Schwarz inequality. And now, because of this, we can actually use this following step, step 2. Okay, so the following step will be step 2. 2x, and this is y plus y squared. This is from step 2. Okay, and now from this we can actually factorize, and then it will be the same as x plus y squared. Okay. If you want to do it step by step, we can actually just go factorize it quickly with another extra step inside. So it's y multiplied by the same bracket. From the distributive law, we can actually know that these two will end up being able to factorize squared. Okay, so this is just factorization. With the dot product. Okay, and our 10.3 asks us, why does step 4 follow from step 3? A full explanation with reasons is required. So how do we get from here? How do we get from here to the following step? Okay, that is kind of strange, but we can actually get there. If you look at 10.3, how does step 4 follow from step 3? Okay, so let's start with what they gave us in step 3, basically. So they gave us x plus y squared is smaller or equal than x plus y. Let's just see if that is what they gave us. Yes. Everything obviously squared. Okay. So let's just put brackets to make it consistent. Okay, so now if we square root this, we can actually use the properties of absolute signs, like saying the absolute sign of this plus this, okay, will be less or equal to the absolute sign of this plus this. Okay, so now we know that since this is going to be it's always going to be greater than 0. So since anything inside of this, let's say anything, this will always be greater or equal to 0 for any A is an element of R n, then this x plus y part, just want to make sure that was actually not intended, x plus y will actually be less than or equal to x plus y. And I think that is what we had to prove. Yes. So they ended up with this, exactly what we ended up with. Perfect. And now 10.4, give a complete conditions without proving when this is applied. Okay, so let's think about this for a moment. Okay, so from the previous one, from the previous thing we did, we see that this part is less than or equal to this part. But when is it actually just equal? So it is just equal when x is a scalar multiple of y, okay, or y is a scalar multiple of x for some alpha is an element of R. Okay, so this is what it is, but alpha is not equal to a zero vector. Okay, because that will be wrong. Okay, so x should just be a multiple of y and y should just be a multiple of x. Then it works, but alpha should not be 0. Okay, that would be a wrong assumption. So for 11, there's only 2 questions left, question 11.1 and 11.2. So find an example of vectors a, b, c, an element of R, okay, such that a times c is equal to b times c, but a is not equal to b. Okay, so both of them should be multiplied with c, but they should not be, they should give the same answer, but they should not be the same. Okay. Okay, so the easiest for this to work would be to let a be equal to 8 to 1, anything, and b should be equal to 1 to 8. So just this backwards. And let c be something very easy and constant. Cool. So 1, 1, or 1. It's very easy to work with. So a times c will be equal to 8, 2, 1 dot 1, 1, 1, which is equal to 8 plus 2 plus 1, which will be 11. And b times c will be equal to 1 to 8 dot 1, 1, 1. This will also be equal to 1 plus 2 times 8, which will also be 11. So a times c is equal to b times c, well, dot c, but a is not equal to b. Cool. Because why are they not the same? Because the components differ. Okay. A and b are not equal because the components differ. Because 8 is not equal to 1. 2 is, well, 2 actually is equal to 2, and 1 is not equal to 8. So the components do differ. Okay. So now for the last question. Let L be a line in R3 if P, Q, R are 3 distinct points on line L. Proves that there exists a non-real number alpha such that this is true. Okay, so we basically have a line with P, Q, R on it. P, Q, and R. They don't say which is in between, so I'm just going to do it like this. Are 3 distinct points on this line L. Prove that there exists a non-zero real number alpha such that P minus R, so these two, that this is a scalar multiple of QR. Okay, so this is going to be something very strange to prove. Okay, let's just start. So let's actually go ahead and use the previous theory we just learned of this. A dot c is equal to b dot c, but a and b do not necessarily need to be the same. So let's say let L be equal to a plus t, and then b minus a. So write it in a way of using the previous one. Okay, and then we say where a is not equal to b, just as we said previously. A is not equal to b, sorry, that was a mistake. A is not equal to b because all of the components are not equal to each other. Okay, so P is on this line, remember? So P is an element of L. So P is equal to A plus T1 and then B minus A. For T1 is element of a real number because this is a line. Hence this. And Q is the element of L. So Q is equal to A plus T2 B minus A. For T2 is the element of the reals. And also we said R is the element of L. So R is equal to A plus T3 B minus A. For T3 is the element of the reals. Okay, so now what is PR? Let's go work that out. So P minus R is what? P minus R will be this part. So this minus this. Let's see what this will be. So it is T1B minus T1A. Subtract this part, which is T3B plus T3A. And let's see how this simplifies. It will basically just be, let's group what we can. So let's group this, and then also this part, and this part. So the T's are together. Okay, and the A's are together, and everything is grouped. So for the A part, we have minus T1 plus T3. Okay, plus with the B part, which is T1 minus T3. Okay, so that is what P minus R is. Okay, we know this now. And let's go work out what Q minus R is. It's just these two subtracted from each other. So this A minus A cancels out basically. That's why I didn't include the A minus A here at the top. Okay, it's just going to be this T2B minus T2A minus T3B plus T3A. And again, we group. We group the A with the A and the B with the B. Perfect. So now the A parts will be minus T2 plus T3 plus with B. Remember those are vectors. And B part is a 2T minus T3. Okay, so that's what we have so far. That is P, and that is indeed R. Okay. What can we say? What else? So since P is not equal, well, Q is not equal to R, since these two are not equal to each other, okay, we can say that obviously because they are two distinct points. Since those two are not equal, then T2 will not be equal to T3. So that's from here. Okay. So those two will not be equal. Now let's say let alpha, so this thing here in front, be actually equal to this relationship. Of minus T1 plus T3 over minus 2T, there should not be a 2 there, minus T2 plus T3. Okay, let that be the relationship. Okay, and we also know here that since P is not equal to R, then T1 is not equal to T3. We know this. And now P minus R is equal to this alpha part times Q minus R. Okay, so how can we say this? We literally use this relationship to work out alpha. Okay, and we just replace this alpha here basically. We can substitute it into there and we will get the same. Okay, so this is what we wanted, and this is then correct. And that was the last question. This last question was a bit confusing because there's like a method to do a proof, and every proof has a different method. But usually start with what you calculated here. Start with the concept of what you did at the previous one. Not necessarily the same numbers, but start with the same concept and work your way from there. And that was it for the semester test 1.